Okay, let us start in this session. Our first talk is from Dr. Marcelo Bacher from Applied Materials, and the title of the talk, When Active Learning Meets Multi-Armed Bandits.
Okay, thank you very much. Good morning to everybody. No, it's not a mistake. It was a change in the agenda, so I'm replacing someone also from Applied Materials. Welcome, everybody. Good morning. My name is Marcelo Bacher again. And what we would like to show you today, it's a little taster of what we are doing at Applied Materials Israel. No. Okay, okay. Understood. Okay. So, first of all, we like to invite you, everybody, to visit us in the stand. We have more information. You can talk to other algorithm developers. What refers to me, I'm an algorithm developer at Applied Materials here in Israel in Rehovot, also leading a team. We are also recruiting good algorithm developers, so please stand by and visit us. One of the questions that everybody asks here is what Applied Materials does. Why are you here and and that's one of the reasons that we would like to show you that we also apply AI, machine learning, image processing, computer vision, as you might already saw or talked to our guys. So let's start what's actually Applied Materials. Applied Materials is the company #1 in the world providing equipment and technology for the semiconductor industry. It's based in the Silicon Valley in the States, the second biggest research and developer center. It's located here in Rehovot in Israel, where we are here. Around the world, name that changes, but it's around 21,000 people around the world and distributed over the world. Also on the customer premises, 12,000 patents. But what actually it's really important, at least for us, the R&D people, is this number, it's a figure here. Applied Materials invested and still invest over the years an amount of profit to the R&D to generate the next technology, the next generation technology for the semiconductors industry. So what we in Israel do, specifically we are almost like the eyes of the fab. The semiconductor industry, it's a very complex one where chips, almost every chips in the world has been seen and checked by applied tools and equipment. And in this complexity, the fab, the engineers would like to know what actually happens, especially when you are going into the nanometer or Armstrongs, even though. So what we provide is image-based diagnosis and control system for the customer through the development of the chips, and also to secure end defect, to detect and classify possible potential defects that may arise through the development of the chips. It could be through the mechanical or some parameters or whatever that happens on the wafers. So in this regard, one of the things that we do, especially what we'll see later, it's based on this little image, just an sample from a simulation. We see here a little point that actually it's a defect from the point of view of the design, and this defect has to be detected. As you can see, the scope, it's around nanometers. That impacts also the length of the optical device that we are using. And the idea is to detect a little bit of that over the whole image. And the area is actually anomaly detection, right? But it's not like finding a dog in a bag of cats. It's finding a dog with a blue eye in a bag of dogs, many, many dogs. And that is what the challenge is about, to have this kind of a lot of images with different angles, and to detect that this is a problem, and that might be a killer for the customer, and that's what the customer wants to know. So, besides this, Applied Materials here in Rehovot, the algo development team, it's around 70 algorithm developers, PhD, masters, several fields, physics, electronics, also computer science, which makes us, or makes the the building where we are working all together, a nice ecosystem. So we can do our own private meetups, brainstorming over the floor, also several meetings when you would like to discuss your potential solution, where although there are a lot of literature papers with those challenges and with those pictures, actually usually the papers don't work. So we have to be very innovative. In order to be very innovative, it's very nice to work in a team. So what do we do? Later on I will start a little bit deep in the technical, but it's important so you can understand the scope of the problem we will address. So we provide process and diagnostic control tools. That's based on two different equipments. One is to detect and classify defects, as we see on the left side. But also we have defects, or not defects, but but we have to measure critical dimensionalities, which is in this case the thin of the path, that in case it will be thinner, it might be generates worm. This worm might be a killer also for the semiconductor in the long term. So according to some specifications, you have also to stand on the design. Of course, there are machines that generate that. What we provide as exactly the eyes to help the customer to see that everything is going on according to the plan. So, how hard can it be? Okay, so let's suppose, maybe not everybody is aware, but a wafer, it's the base where the chips are constructed, built, developed. It's a very thin disk of silicium, comes from the sun actually, and over this silicium there is kind of a mesh, and every one of these is a chip. That could be a controller, memory, microprocessor, DSP, whatever you like. And of course it's a copy-paste, so a lot of them will spread around the wafer. The dimensionality is the 300 millimeter wafer, and we are looking for that guy here in around 30 nanometers. So if we scale out this image, it's like finding an ant, the color, the direction, from a satellite view from Manhattan. That will be exactly the same scope, the same scale that we are looking for, and we have to do it fast. What's the meaning of fast? Well, the inspection, it's a sampling. And when you do inspection, you have to take a wafer out of the fab, more or less, revise it, check it, and then put it back on the fab. That takes time, of course. And the scope of the time is around 5 to 7 minutes. We have to scan all the wafer, make the detection, and classify it. So that's the way of the challenge. So how we do that? Well, one of the equipment that are also developed and also from the scratch until supplying it at the customer premises, it's an optical inspection review based on lasers. It scans very fast all the wafer, generating pixels of around 20 to 50 nanometers, depending on some specific parameters. So this guy scans a wafer, generating around a billion of pixels. Actually more, but after some processing, it's like a billion of pixels in around 10 minutes, more or less. So the images that we get from this guy are here, 2 samples, for example, depending on the angle, also from the reflection of the laser. So in this case, we can see from a little point here, there are also, maybe that's in a logarithmic scale, it would be actually better. But if we make a picture with a much higher resolution, we'll see a scratch, this scratch. But what we'll see are billions of points of that intensity. So that's the start. So we have to detect the problems, or at least to understand that there are problems, and then we have to figure out what is this about. So due to Moore's law, I don't know if you're aware, but every year the integration, the volume grows almost exponentially, or double, so it's exponentially over the time. Over 5 years ago, it will be actually easier, let's put it in that case, because it's still there nanometers dimensionality here. It was easier like to put a threshold and say, okay, if some signal to noise radio go over some threshold, then we are actually facing some defect, potential defect. Later, the customer will decide if it's important or not. But over the years, this curve started to shrink, mixing up the effects that we want to check with the nuisances. So like the distribution of the two words are starting to merging together and blending together into one big distribution. What generates, it's going from a relative small amount of data that we have to collect to a large amount of data where actually everything here is mixed up. So that is the scenario what we are here when actually it's getting worse. So in order to capture this specific, for example, the scratch that we see before, we have seen before, we use another equipment also developed at, in Rehovot, applied Israel, which is an electronic microscope. It's not like a microscope. We are talking about like a 20 square meters machinery. And this guy can generate those kind of pictures with very high resolution, almost no noise, but takes time. And again, in time is money. It's not like it's a joke. It's in this case, it's really time is money. You can't afford the customer or ask the customer to stop several wafers and see what happens. If we would like to use this machine, because we could, and scan the whole wafer, will take around 3 weeks to generate the same amount of data that we can generate around like 10 minutes, but with a higher resolution. So now we are having two machines. One is generates a lot of data. The other can tell us a little bit more about what we are actually checking. And if we put all those machines together, what we see is on the left side, we have a low resolution or relative low resolution image from an optical microscope, generates a lot of data. Then we do some sampling, some magic here, and then take these samplings to this same vision or the high resolution electronic microscope to try to figure out what's going on inside there. There is a classification process and there is a detection process. Detection is here, classification is here. We learned here some model, could be a classifier, could be a distribution, whatever actually fits the target of our problem. And then we ask ourselves, can we apply this model that we have just learned to the rest of the data to extrapolate the results that we have received and inform the customer how many prognosis, more or less, how many defects are living in the wafer, or should we go back and do some more sampling until we converge to some value that actually would be acceptable? And by the way, this has to be fast, and this has to be under some premises, and the premises is the budget. What's the budget? We can't afford to sample billion points here. We have to sample around 1,000 to 10,000. So the order of magnitude that we have to reduce the information, or not the information, but the data in order to collect information, it's huge. And this budget actually is the limiting factor of the whole machinery. But if we like replace this title here, and we replace some machines, we are actually in the framework of active learning. We have we start with some unsupervised data, unlabeled data completely. We do some sampling. We have our oracle that gives us some label information. Then we learn something with this label, and then ask ourselves, we apply the model, or go back and make another round of sampling. It's exactly the same. So we start with a lot of data that's completely unclassified. We have a limited budget that we can sample. So the motivation goes into the this transformation of the data. We can, as an unsupervised scenario, we can start like clustering some feature space. Doesn't matter if this feature space comes from image processing through some layers of deep learning, could be variational autoencoder. We can sample the latent space, wherever it fits our necessary. We just cluster the data. Each data or each cluster holds a different number of defects according to some feature space. And the balls are at the beginning completely unknown, right? We don't know which one is a defect, which one is actually a nuisance, but they are spread around these 5 jars. So the question is, okay, we have 5 jars. which one should we choose in order to sample, and how many balls we should sample. So we have to start thinking about, okay, we can have feedback, use this feedback as information in order to do the next round of sampling, but we also would like to explore other jars. Maybe we start here, and then we would like to see what happens here. This trade-off, it's called exploration-exploitation trade-off, and it's completely sealed down in a framework what's called, this is the case, it's called Multiarmed Bandit, so we'll see later. But let's suppose that this is the ground truth. At the end, we would like to have a strategy that tells, from cluster 5, you don't need to sample anything. From cluster 3, a little bit. Cluster 4, tell me everything what's going on there. And the other, just to make a little bit from here, a little bit from there. That is the goal. And again, this goal is encapsulated in the Multi-Armed Bandits framework. And that's where we are going now. So this guy tells us, okay, you can develop some algorithm to trade off the exploration exploitation under some boundaries, some mathematical conditions. It's an online optimization, and the idea is to maximize the reward. So we have to define what's the reward in our case to find the green balls. The maximal amount of green balls, that's our reward. And that's what we want to maximize. What's the exploration exploitation? Okay, which jar we are going to choose? In our case, specific case, is actually what's called a full information Multi-Armed Bandits, because we are going to sample all the jars. And because we are going to select not one ball, but several balls also from each one of the jar, we are talking about a multiplay, full information Multi-Armed Bandits. But this was shorter, actually. So, going back to the framework, a lot of data. We have here Octopus. I mean, this Octopus was actually replaced, but it's where the Multi-Armed Bandits, I don't know if you are aware, but it comes from an idea. You come into the casino with $100 in the pocket, and you have to select some machinery. And there, if you look Multi-Armed Bandits in the internet, you will see an octopus like playing around with machines, and this is the guy that will select some jars and many balls from each one of the jars. So that's our oracle, and we have to learn something about the distribution, about the performance of selecting and also retrieving the green balls that we are to find. Great. So a little bit math, just a little bit, not too much. We define in the scope of Multi-Armed Bandits, we have arms, which are actually the clusters. We are free to choose, in this case, what we would like to know. We are aware that the green balls, they are green that's a little bit much green, light green. There are different classes of green. But for us, in this scope, they are all greens. So it's a binary classification problem, in this case, where the green, if we find a green, we will get 1. Otherwise, we'll get 0. Okay? We have a defined budget B, which is from the total number of balls. We would like to maybe do in several iterations. So this number of balls we're going to cut up. We are assuming a Bernoulli distribution because of the 1, 0, and that will also impact in another prior information that we would like to model from each jar. And the idea is to maximize the number of green balls that we detect, and also, in this case, for this specific project, to coverage the full feature space. Why? We don't have only to, thank you. We don't have only to find the biggest amount of green balls. We also have to ensure the customer that we know what happens on the wafer. So also, the jar that was empty of green balls, we have also to tell him that that jar doesn't contain any green ball. And that is maximize the exploration of the feature space. So, in that case, we are adding to the concept of Multi-Armed Bandits classic a force exploration element. This is completely compatible with the active learning paradigm. That's the heart of the problem, and we approximate this problem through an heuristic. We estimate the performance of retrieving green balls over the gray one through a Bernoulli distribution using a beta prior conjugate distribution. We will use the Thomson sampling in order to draw these weights that will later on be used in order to select how many balls from each jar. And that's a STP-KT, which means how many balls from a jar key at time t will collect each time in each iteration. So this is a framework, and it's a general framework. That means that whatever, if this is a DOI and this is anomaly detection, you can also can also be used in another kind of framework. But still, it's a framework of sampling data from different jars, from different feature space, to see what's actually going on and to try to build a model with less amount of data. And that's the active learning issue. So we have t iterations, which in that case, for example, if our total budget will be 1,000 effects and we'll sample 100 times the B, then it will be 10. So we iterate 10 times, then we have to stop. We obtain some empirical reward, which means how many green over how many I sampled. We model as average and some deviation. We enforce here the exploration using a logarithmic descendant function. That means if I sample a lot of one jar, in the next one I would like to sample less, because I already have some information that doesn't contain the green balls that I'm looking for. So then we will model those distributions through a beta, which is the conjugate prior. We will throw from those beta distributions using, for example, epsilon greedy. So we can add a little bit randomness in the selection of these distributions. Then we combine those weights through a convex factor, which is this eta, which means if eta is 1, which means completely exploitation. And if eta is 0, I want just to explore. And then this is the trade-off, how I assume this eta. And it also can be learned. You can also ramp it up from 0 up to 0.9, for example. So you start just exploring, and as long as you get more feedback, you start learning some model and then just go into the grid. Pulling the arms means I selected B balls, from some of them from every jar, select to the oracle, send to oracle, get the feedback, and update my model. So some results. In this case, synthetic, we generated just 50 segments. Each one, it's a number of balls that we have selected, completely randomized. But we also put 3 of these jars containing the much more number of green balls than the other ones. So the idea is to maximize the reward, to recognize that we have 3 arms here we will collect from each one of them, but also we recognize that we have 3, and then we will maximize the reward. That means the number of green balls will be maximized if we apply our hypothesis on the case. And that's what happens, actually. So use this as a benchmark that we found in the literature from 2015, which is the closest paper that we found to our approach. And this is for different eta combinations. And then we see that in all of them, even if we go completely greedy, in this case, we do a little bit better in the reward. It's a logarithmic scale. In this case, real data. This is from the fabric, from the real wafer. Usually, if you do some random sampling, it will trap something. But because of the amount of data that you are dealing with, it will become very, very hard to find something. And this is in the case you set up 2 different parameters. 2 runs with different parameters. And of course, this is completely greedy. And this is how you win. It's kind of counterintuitive, but it's that you win more for exploring a little bit. That means that 30% of your budget goes into the exploration. That allows you to trap more green balls than going just greedy, as using just Thompson sampling. So, conclusions. This is an active learning strategy based on Multiarmed Bandits. Thompson sampling is the engine that we use in order to decide how we handle the budget. We add this additional exploration term. There are other reasons, actually. The number of green balls with respect to the number of gray balls, it's very, very small. So the performance of the Bernoulli is very, very small. So if you use just Thompson sampling, you will just get 0, almost 0, if you draw. So this also enforces this exploration factor. And it's very, very fast to implement. In 10 lines of code, you're already done. So it's very, very fast. It works very, very well. So I'm almost done. Follow us. You can find us in Rehoboth. And stand here. You're also, again, welcome to visit us. LinkedIn, Facebook. And you can also check up what's going on. We are hiring. Thank you.
Thank you, Marcelo, for exciting talk. And we have time for questions. Okay.
When you use the jar, the balls, actually it's the feature space. And this feature space is collected as you would like. If you are working with pictures, you generate this feature space with some mapping or a feature instruction through a deep network or whatever you would like to use. Moreover, you can also assign to each jar some features, specific features that tells you more information than just the feature space. And you can use also these features in order to perform what's called contextual multi-armed bandits. So you get not only the information from the feature space, but also the information from the state of the jar that you can use later. Exactly. No, in this case it's a very good question because usually there are correlations between jars, but no, we treat each jars independently. That's a good question. The false negative. If you miss you think about it. I mean, you get your iPhone with a chip that has a defect. You're pissed off, right? You don't want it. The fab also doesn't want. He doesn't want that any single defect goes until the end of the fab. So you pay a lot of false alarms in spite of reducing the type 2 error. Yeah, definitely, yeah.
Let us thank our speaker once again.